In this video, I'm just going to fairly briefly explain and show why the moment of inertia is based on mr squared, because it does seem a little bit strange that it's r squared and not, just r, for instance. So how does that r squared come about? And to help us out, I have two long thin rods, once again massless, so the red and the blue rod are massless, but we've put a point mass of m at the end. This rod is just L, and I'll call this rod 1. And rod 2 has a length of 2L, so the mass is further away. But in both cases, I've made it so that the force that we're applying is just L from the axis of rotation. So what we can do then is do some calculations for the work. Once again, I'm going to go with work for this. Work is force times the distance, and as we've previously explained, this distance that the object travels is just going to be equal to the angle through which the object travels, or I should say the angle through which the force is applied. So if we apply it over this angle, we get a particular distance, which is theta times r. Now what I've done in this case is I've tried to make it as straightforward as possible by putting all the forces the same and all the thetas the same. So we're going to just rotate it through the exact same angle, approximately at least. So something along these lines. So that's my theta. And if we have the same angle through which it rotates, and we have the same distance for the force from the axis of rotation, that means r is the same. So W1 equals W2. This is different from the previous video where we had them different from each other, but I've kept everything the same. So we have the same amount of work being done in both cases. This will allow us to do some comparisons and substitutions later. Let's first define what the work looks like for each case. So work 1 is force 1 times distance 1. And force 1 is just equal to m times a times x1. And I'll call that a1 and x1. And what we can do with a is we can make that equal to alpha times L. So this is the acceleration of the mass, so it's alpha times L. If we look at the distance through which the object is moving, we get theta times L. And so we end up getting that the work done on the mass is equal to, and I should be clear here, this is the work done by the force, right? And this is the work done to the mass. And the difference is that here we're looking at the force being applied, and here we're looking at the mass and its acceleration and its distance. So this distance here is the actual distance that the mass moves. This is the acceleration of the mass. This is the mass of the mass. This up here, this stuff up here, is actually the force being applied and the distance over which the force is applied. So these are actually two different x1s, and I should have been much clearer about that, but I apologize, I was not. But they are different because here I'm focusing on the mass. So we have alpha times L, theta times L. Now if I take this mass here, multiply it by those things, I end up getting ml squared times theta alpha. And if we look at the second mass, we know that it's F2 times x2, where once again these are force and the distance of the force, but then I can rearrange this a little bit and substitute in. So this is m times a2 times x2. And so when we're looking at what's going on to the mass specifically, right? What's its acceleration going to be? We have m times alpha 2 times L, times 2L, and then we have theta, which is just the same for each of them, times 2L. Why times 2L? Because it's moving through a distance of 2L. And I'm just going to go back and label this an alpha 1. Now, why is it 2L again? Our force is only moving through a distance of theta times L, but we're no longer looking at the force. We've switched gears to focus on what is the mass doing. The mass itself is moving through twice as much different distance, 2 times theta L is the distance through which it moves, not theta times L like we had in the first case. So we have to plug in the 2 times theta L. And what this gives us then is that we have 4 times m L squared alpha 2 theta. What this suggests is because we know that the works are equal to each other, we can set these two equations equal, and we then get, if we set them equal to each other, ml squared times theta times alpha 1 equals 4 ml squared alpha 2 times theta. Everything cancels out except for a 4 and of course the two different alphas. So we get that alpha 1 is equal to 4 times alpha 2. So we get 4 times as much acceleration. Now if we just kind of finish this off, if we're saying that torque, the sum of torque, is equal to I times alpha, and we're not really sure what the heck I is, the first thing we notice is that by simply keeping the same mass, applying the same force at the same distance, keeping the same mass, but having that mass have to move through twice as much distance, we see that we get 4 times the acceleration in the first case than in the second case where the mass is twice as far away. The only thing we varied here is the R value for the mass. Instead of being located at L, it's located at 2L. And so, if we solve for I being equal to the torque divided by alpha, one of the things that we'll notice, hopefully, is that we end up getting a relationship with mr squared. And hopefully we can see this just by looking at this. So if this is the work that's being done, it might be good to recognize that work equals force times distance, which is the same thing as torque times theta. So what we have here is torque times theta, which I can then say is I alpha theta. And so basically everything other than the alpha and the theta make up this thing that we call I, which we didn't really know what it was at first, but now we can see that it is related to m times the distance of the mass from the axis of rotation of the mass from the axis of rotation squared.